homolysis, as we saw earlier. So this X can form a X double bond Y along with the removal of Z dot, right? So here similarly we see that the spin is transferred from X over to Z dot. So these are something very interesting. That means you can use spin transfer type of reactions and make radicals very easily, right? This is an example, right? So this is one of the example of substitution reaction. This is another example, as I just showed you, radical addition. Bromine can add over here, over this alkene, to form this type of a moiety. Now the question is that bromine, this free radical is adding to this position, but this bromine is not getting added to this position. So this will be called as a regioselective product. Bromine is forming, bromine is added over this moiety, and this is the major product. What is his reason for it? As I told you from my outline, that radicals are very small, and this can actually give us chemoselectivity as well as regioselectivity. Why this major product is forming, but then why this bromine radical is not getting attached to over here and this being over here? Okay, this is
Stability.
because this
Due to stability.
no, it's a tertiary radical. Exactly. Very nice. Very nice. So it's a tertiary radical. That's the reason it will always try to stabilize during the reaction pathway, and then this product is formed because the transition state is also much lower in energy, and this product is formed as a major product, and this now can further propagate to form its products. Similarly, as I gave you an example of radical addition in my last slide for ethyl radical. This is an example of the elimination, the third type of a reaction, and I think you all know this moiety. This moiety is called the azo-isobutylonitrile. In short, it is called AIBN. Azo, because of this N double bond N moiety. Isobutylyl, because four carbons are there, one carbon, two carbon, three and four. So isobutylyl, and then N is for the nitrile. C triple bond N forms the nitrile. So this molecule is used as a radical initiator. So this can start radical reactions. So you can use light as you always as, or you can use heat to form this product. You can easily see two equivalents of this moiety is forming, right? Because of this bond breaking of this carbon nitrogen bond, and then this nitrogen nitrogen bond is formed. This reaction is driven by entropy. This reaction is also driven by enthalpy because a very stable nitrogen molecule is formed. Nitrogen molecule, you know, has a very strong bond energy, more than 940 kilojoules per mole. So that's the reason this reaction is driven by entropy as well as entropy as well as enthalpy. So this reaction can be driven by heat as well as by light. Here I have given an example of a thermolysis reaction of the AIBN. So this is the radical form, and this can initiate reactions. Similarly, dibenzoyl peroxide, as I gave you in the example in the very beginning of the bond dissociation energy, can undergo homolysis, and then a radical elimination reaction to form a phenyl radical, and then again a carbon dioxide gas can form, giving higher entropy of the system. And that's the reason that benzoyl peroxide can be easily heated and made into a benzoyl peroxide radical, and then radical reactions can be initiated. So these are the major three types of reactions which I showed you: addition, substitution, and the elimination reactions. Now, very important part of the radical chemistry where we have to understand is the frontier molecular orbital. That means the orbital, molecular orbital picture of the radicals. And the best thing is to start with the methyl radical, CH3 radical. CH3 has three hydrogen, right? And all the three hydrogen you can think of it is degenerate. That means these orbitals, right? The sigma carbon hydrogen orbitals are of same energy, right? And the unpaired electron in the methyl radical is existing in an orbital which is called the singly occupied molecular orbital or called the SOMO. Up to now, I discussed with you HOMO and LUMO, highest occupied molecular orbital and the lowest unoccupied molecular orbital. But here, you first time you see that there is also a orbital in a radical where one unpaired electron is there because methyl radical has this one electron coming because once you are dissociating from say a CH3Br or CH3I, right, that one of the one pair electron has come over the carbon. So now this is the unpaired electron over this orbital, and then these are the higher energy vacant orbitals, these are the unoccupied sigma star orbitals. So this is a very simplistic molecular orbital picture of the methyl radical. And you can easily imagine that why these radicals are so unstable, transiently formed, is because these electrons can easily pair up in under with water, pair up with the solvent molecules, or any molecule it is seeing under the conditions. That's the reason radicals are extremely reactive. Let us also understand in this way, greater the value of this delta G, that means the energy required to homolize these bonds, right? So that means greater value means stronger bond, right? So it is not easy to form this X dot Y dot. And the energy released in combining these radicals, that means greater value means higher energy and more unstable radicals. So this is the another way of understanding. That means as we have already seen that XY, if it is very weak, we can easily get these radicals, and if the XY is strong, right, this molecule will be very difficult to make into the radicals. So this is a very simple understanding which we have already discussed, but this is the basic thing about the radical stability. This is one of the very important slides, and this is based on this bond dissociation energy. A methane molecule can form this methyl radical. You can see this methyl radical, but has a bond dissociation energy of 439 kilojoules per mole. But then on the other hand, a primary radical has a bond dissociation energy of 423, and then a tertiary radical has a bond dissociation energy of 397. From here itself, it is very clear to you that it is much easier to break this bond in this type of a tertiary butane rather than a methane molecule to break this bond. So that means the tertiary radical, because of also of the hyperconjugation and its steric nature, right? Bulky methyl groups, tertiary radicals, carbon-based radicals are much more stable than the methyl radical, the primary radical or the secondary radical. So radicals can be stabilized. Please remember, because of its structure, two things are important. One is a kinetic factor. The kinetic factor is controlled by the sterics of the group. So these groups protect these unpaired electron, as well as there is also the possibility of hyperconjugation to stabilize this tertiary radical as well as in the secondary radicals vis-a-vis to the primary radical. So that means from the bond dissociation energy as well as from the kinetic stabilization as well as thermodynamic stabilization, this is a very simplistic picture that how structure can actually allow us in the organic molecules to stabilize the radicals and have a longer lifetime of the radicals. Of course, the radicals, you have to find it out that yes, how much is the lifetime of the radical, how much time it exists. Does it exist for microseconds, femtoseconds, or it exists for hours, for days, or it exists up to infinite time? The radicals which exist up to infinite time are very, very rare, and you require some very, very judicious or uh, very, very novel design concepts to stabilize the radicals and keep them on the bench. So now I move on from this slide to this type of radicals. You can see that vinyl radical, alkyl radical, or phenyl radical will be much less stable than the alkyl radicals which I just discussed. Similarly, allyl radical, which I have already discussed with you in the case of that reaction, right? Uh, allyl radical as well as a benzyl radical will be more